Hello everyone. Today we will see some properties of multivariate normal distribution through our practical. So let me first start with a four-variate normal distribution. If you remember, we have already learnt how to draw a sample from multivariate normal distribution in the last practical. We are going to use that here and build on that to prove some more properties. So suppose I have a four-variate normal distribution with this mean mu and this variance covariance matrix sigma. First we have to verify that sigma is non-singular. I don't think I need to really show that. You can just compute determinant of sigma and it would turn out to be non-singular. Then draw samples of size 3, 4 and 5. For each sample compute S matrix and check whether it is singular and comment on your findings. Okay, so what happens is actually there are no new commands involved in this question, so I'm not going to do R coding because anyway it's drawing a sample from multivariate normal, which we have already done, and checking singularity will just compute the determinant, so the command det. Now what happens is, if your setup is such that your n is less than p, that is the number of observations is less than the number of variables, then you end up getting a singular sigma. Okay, I want all of you to check this for this particular matrix. I know manually it's going to be slightly difficult to compute determinant, but it's not impossible, and I guess you have a lot of time. So do compute this sigma, and you don't have to actually take a sample randomly. Okay, so you know the mean, so around this mean just roughly take any 3 observations. Okay, if you take any 3 observations and compute sigma from four-variate normal distribution, that sigma would turn out to be singular. Sigma means sigma hat. So in fact your CSSP matrix itself would turn out to be singular. Okay, so try to verify this by doing manual calculations. We will move to the second question. Second question is important. Obtain a random sample of size 100 from a normal distribution with this mean and sigma. So mean is 1 and variance is also 1. Assuming sigma square to be known, plot the likelihood of the above sample as a function of mu and obtain MLE of mu. So instead of obtaining MLE by direct method where we know that x bar is MLE, we are going to see by plotting can we get an MLE. Okay, so let us do this in R. So I don't know whether you have noticed, but in this particular exercise we are having univariate normal distribution. Okay, so it's a univariate normal distribution. Okay, so my mu is 1, my sigma is also 1. Let my sample will be R norm, n is 100. We are supposed to obtain a sample of size 100 with mu and sigma. Okay, so let me run this. I have a sample. Now I want to compute likelihood. Okay, so what is likelihood? Likelihood is actually PDF of normal, product of PDFs. Okay, so PDF is given by D norm. So D norm I have to compute at S, and with which mu and sigma, that is the key. In likelihood, we assume that likelihood is always a function of parameters. So here it would be function of mu and sigma, which we have to input. Sigma, it has been told to us that okay, sigma we are supposed to assume as known. So sigma we would keep as 1, and we have to plot the likelihood as a function of mu. Okay, so let me write the command for likelihood. So we will create a function which is a function of mu. Let me call it m because I already have a mu defined over there, and my likelihood would be L I K E L. Suppose likelihood is this. D norm S, mean is mu and sigma is, mean is m because we are creating it as a function of m. Of course I want to take product. Okay, let us try to see if this runs. Sorry, let me try to compute for, let's say, actual mu. Okay, I'm sorry, my function is not like L, my function is L, and it is safer to add a return command always. So okay, so see, this is the value of the likelihood. If you can see, it's very small, 10 raised to minus 62. In fact, that is one of the reasons why we generally go for log likelihood. So let me modify this function, log likelihood. So instead of product, I will take sum of log of this. Okay. In fact, there is a direct option we can have here, log equal to true inside denom, but we won't worry about it. And this is log likelihood, so let me call it LLL. Okay. And now let us compute. Okay, so this is now a reasonable value, but we have to plot this as a function of mu, because that is what likelihood tries to do. We try out different values of mu and we try to see at which value of mu we get the maximum thing. Okay, so let me try different values of mu between, say, 0 to 2. So let me construct a sequence between 0 to 2 of length, let's say 100, and then for each of these I'm going to compute the likelihood. So for I in 1 to 100, we will store the log likelihood. Let me create a vector to store that, named log L. So log L at I is likelihood with mean taken as ith entry from MSEC. Okay. Okay, let me run this. Okay, so log L we have computed, and let us try to plot. So let us plot MSEQ with log L. Let me take type equal to L because it's better to see a curve. Okay, see, this is a convex function, so somewhere near 1 there is a maxima. Exactly getting maxima in a graph is a bit difficult, so we can go for the command. So we can say which dot max of log L. So this would give me a place, simply max. Okay, let me show you both the things. Simply max of log L would give me the maximum possible value of the likelihood, which in this case is 140 point something, minus 140 point something, but I am interested in which mu gives me maximum log likelihood. So if I run this, I'll get the position, and I want to see the mu, so we will say this. Okay, so in mu sequence at 45th position, whichever mu is there, that is giving me the maximum value of the likelihood. So it turns out to be 0.8889. And we know from our theory of normal that x bar is actually the MLE. So x bar, let me compute. So it would be simply mean of S, and x bar here is, see, it is quite near 0.88, 0.89. Now one question is, why didn't I get exact same values over here? Okay, why do the values differ at the second decimal? Can you guess? See, the thing is, we are not trying every possible value between 0 to 2. We are trying in a graph only 100 values between 0 to 2. So instead of this 100, if I try many more values, let's say 10,000, then let us see what happens. Of course, the code takes slightly longer to run. The graph, I don't think there would be much change, because anyway it was a continuous function. See, now we are more close, 8908, 8909. So up to third decimal we are matching. Instead of 10,000, if I make it say 5 lakh, then let us see what happens. Oh, sorry. It takes slightly more time to run. Okay, because I'm on a laptop, not on a workstation, so it's definitely going to take time. Okay, so yeah, graph I shouldn't have drawn because fine, anyway the graph is not going to change, so it would have been okay even if I had dropped it. See, now 890918 and my x bar is 89090, so up to 5 decimal now they are matching. Is it okay? So this is how you actually, this is how MLE works. You actually try different values of the parameter and see at which value of the parameter the maxima is there. If you want, you can indicate this value in the graph. So maybe I can draw a vertical line and horizontal line at both these places. So maximum of log likelihood, I will draw a horizontal line there. So AB line H equal to this, okay, and then AB line V equal to the point at which the maxima is attained. Okay, so this way I am indicating the maxima in the graph. Okay, so same story we have to repeat with sigma. Assuming mu to be known, plot the likelihood of the above sample as a function of sigma square and obtain MLE of sigma. It's exactly the same code. Okay, now let me move to question 3. In question 3, we are going to use the property related to quadratic form of multivariate normal. If you remember, we have proved that x minus mu prime sigma inverse x minus mu follows chi-square with p degrees of freedom. So we are going to verify that. For that, first we have to draw 100 samples, each of size 50 from above distribution. When I draw one sample, I will get 50 values corresponding to this quadratic form. Why? Because my sample size is 50. So corresponding to each observation, I would get one value. So overall, I would have 50 values. Now from these 50 values, I can check the distribution. So I can try to examine whether the distribution is chi-square p by testing. Okay, so what I'll do is, I'll apply Kolmogorov-Smirnov test to these 50 values, this sample of size 50, and I would check whether the distribution is chi-square 2, and I would repeat this exercise for 100 samples. Why not stop at just one sample? Because there are two possibilities. If you are, one possibility is, okay, even if the sample is actually not from chi-square, by fluke you got chi-square, or reverse way, the sample is actually chi-square, but you are unlucky and you got the test to be rejected, because you know that for any test there is going to be type 1 error and type 2 error associated with it. Okay, so what we are going to do is, we will draw 100 samples so that we'll have repetition, and ideally as per our as per our result, it should be chi-square and the type 1 error should be at most 5%. So roughly for 95 samples, we should get the chi-square hypothesis to be accepted. Okay, now for drawing a sample, let me use our old code, the code from last, the code from last practical. Okay, so this is the code. We will just change mu and sigma and we'll use this code. Okay, I don't need all these things, I just need the matrix, the data matrix. Okay, my mu is supposed to be 41. Oh, I think I've used the same 412 minus 1 minus 1 5. Yes, okay, I don't need to construct T matrix manually. I can use the Cholesky decomposition matrix. Now my sample size is supposed to be 50, p is 2, and I have to repeat this whole exercise 100 times. So let me make number of simulations as 100. So these are known as simulations. When you draw multiple samples, you call them simulations. So by simulation, you are trying to verify a theoretical property. So for k in 1 to n sim, this is not going to change, so I'll keep it outside. This I need to keep inside because for every sample I need a new IID normal 01 observations. Okay, otherwise I'll get same sample every time. So this needs to be inside this K loop. Okay, so for every simulation, what I'm going to do, first I'm going to draw a sample from standard univariate normal, then I'm going to transform that sample to multivariate or bivariate normal. Okay, and on that bivariate sample I have to compute this quantity x minus mu prime sigma inverse x minus mu. So let me do that. In fact, we can do it inside here also. So let me call it QF. QF is a blank vector to store the quadratic form. QF at I would be x is my this, so y x minus mu prime sigma inverse, so sigma inverse x minus mu. Okay, okay, x minus mu prime sigma inverse x minus mu. So I'll compute it for every I. So at the end I'll have 50 values of QF, and to them I have to apply chi-square test. Let me do it for one sample first. Okay, so suppose I have this Z. I need to run all these things first. Okay, so I have got QF. Just to show you whether it is actually like chi-square, let us draw histogram. See, it looks similar to chi-square. In fact, we can draw a density plot instead of histogram. So plot of density of QF. By the way, this is not chi-square density. This is density estimated from the sample without assuming any distribution. So this is actually known as non-parametric density estimation, and one of the methods for that is of course via histogram. Another method is via kernel density estimation. So this is what R is using here, kernel density estimation. See, does this look like a chi-square graph? If you are not sure, let us try to overlay chi-square graph on it. So lines, we need chi-square density, so d norm at -2 to 10. So ideally chi-square would start from 0 to 10. So let me take a sequence from 0 to 10, length equal to 1000. Okay, and we need to compute chi-square at this. So chi-square PDF will be d chi sq at SS with degree of freedom equal to p. Okay, and we will plot this. So SS along with its PDF. Let me plot by different color. Okay, I have some error. Oh, SS I did not run. I'm sorry. So SS. See, at least for this part it is matching. At the beginning it would begin from 0, of course. So in non-parametric estimation, since it is not perfect, it takes negative values also, but roughly the shape is like chi-square. Okay, Okay, but of course we can't draw graph and rely on it. Graphs are always subjective. So we will go for test. So I can carry out Kolmogorov-Smirnov test to compare it with chi-square. So p chi sq and degrees of freedom equal to 2. Okay, so you can see here the output of the test. The p value is this. So p value is greater than 0.05, means the test says that the chi-square assumption is accepted. Now if you remember, we have to do this for 100 samples. So I have to repeat this and I have to store the p-values so that at the end I can see out of 100 how many samples actually turned out to be chi-square by the test also. Okay, so let me just store p-value from here. Let me store it in a vector called p-val at k. Why k? Because this is corresponding to kth sample and I am going to have 100 such sample. NSIM is 100. Okay, so I need a blank vector to store p-values. Okay, fine. So what I am doing, let me revise. First I am constructing a Z matrix which is standard normal univariate random variables. We are transforming them using YMAT. We are transforming them to bivariate, and then for each bivariate sample I am going to construct this quadratic form. Okay, x minus mu prime. So I will take every x, that is ith observation, bivariate observation, mu prime sigma inverse x minus mu. Let me run this now. Okay, now we have to see out of these 100 samples, for how many samples p-values are less than 0.05. That is, for how many samples the chi-square assumption got rejected. So okay, so it is 11. So it's ideally it should have been 5%, but again in sample anything can happen. Okay, if I run this again, my answer is going to change. See, now it is 4. Okay, so it should be roughly 5%, means if you do this entire exercise, if you do too many times, and if you take average number of times the p-value is less than 0.05 out of 100, then it should be near 5. Okay, so this is how we have verified the chi-square assumption. And now the last question is, consider the last sample from the above question. Plot the log likelihood of the above sample with respect to a range of possible values of mu, assuming sigma to be known. Locate the maxima and compare it with the maximum likelihood estimate. Now if I want to plot this, I would need a 3D graph, because now my mu is bivariate. So I have two components, mu1 and mu2. So on my x-axis I would have mu1, on y-axis I would have mu2, and then I would have the log likelihood on z-axis. Okay, so let us try doing that. We are again going to use outer now. That way we will get some practice of outer. So mu1, we know the actual values of mu. So right now I can try to be around them. In reality you don't know that. So you compute sample mean, which is MLE. So you try to plot likelihood around that region. Okay, so mu is 4. So let me take, and sigma is 2 here and 5 here. So here variance is square root of 2. So 1.4. So let me take mu from say 1 to 7, mu1 from 1 to 7, and mu2 from say, I don't know, minus something. Let me take, okay, mu1 we will take from 1 to 7 and length equal to, let me say, 100. Mu2 let me take from minus 2 to plus 4 and length again 100. Okay, I need to write the likelihood. We can use the bivariate PDF that we computed last time. So yes, I have that here. So bivariate PDF we had computed, so we can use that function. But now, oh sorry, the thing is, when I computed PDF, it was function of xy. Now I don't want to compute PDF. I want to compute likelihood, so it has to be function of mu1, mu2. Okay, so let me call them m1, m2. Sigma is known, we will use that. V we won't take. Okay, so let me call it bivariate likelihood. So every time instead of V, we are going to take ith observation from that sample. So VB y mat, my m is small, so y mat ith observation. Okay, so I have to do this for I in 1 to n, because while computing likelihood I have to compute PDF for every observation and then take the product. Okay, so this is first term. Now instead of mu, I would say, okay, let me call it m hat, not hat actually, m try, because it's not estimate, we are trying different values, m1 comma m2. So I would say m try sigma inverse m try. I know I'm going slightly fast, but now that we are not in a class, you can pause me anytime you want. Okay, in the class also I give you that option. I do ask you to raise your hand and stop me, but of course in class it is difficult. Here you can pause, you can try to repeat whatever number of times you want. So I think it should be okay. And this way you would also, you can also try increasing your own speed. Okay, so what I am doing is, for different values of mu I have to try, so I am calling that value as say m try. I'll compute this t1 into t2, but of course we have already seen that computing likelihood is generally risky because it's very small, so we go for log likelihood. So instead of saying this, I would say return log of t1 plus log of t2, and I won't return this, I have to store this because I have to try many possible values. Okay, so this log t1 plus log t2, I need to compute this quantity for every observation. Let me call it say log L at I, and finally we are going to take sum. So at the beginning I should define log L as a blank vector, and then the actual log likelihood that we need to return is sum of PDF for each, sum of log of PDF for each observation. Let us try to see what we are doing exactly. So we are trying to compute log likelihood for some mean, for some value of mu, some possible value of mu, which is denoted by m1 comma m2. So what we are doing, I am taking ith observation, then I am computing PDF at ith observation, taking log of it. Okay, I don't need this bracket, I can delete it now, and then I have to do this for all n observations, keeping my mu constant. Sigma anyway we are assuming to be known, and we will return this final log likelihood, which is sum over log likelihood of all the observations. Okay, so let me try to run this first for a few one or two illustrations. Okay, so if I try to run this by LL at my actual mu, okay, I should get some value. Okay, I'm getting some value of log likelihood. Is it okay? Now I have to try many possible values between this given range of mu1 and mu2. So if you remember, outer command is going to help me do that. So in the outer command, I'll consider all pairs of mu1, mu2 from this range, and then we will compute log likelihood over them. So let us try that. Let me call it LLMat. So outer M, what did we name them? I think mu1, mu2. Yeah, mu1, mu2. So outer mu1, mu2 and vectorize of log likelihood. Okay, you remember why we want to vectorize? We want to vectorize because we are passing mu1 and mu2 as vectors, but we want to tell the likelihood to take them as, to extract single elements from them. Okay, so this is going to be ideally 100 cross 100 matrix. It's taking time because it is doing 100 into 100, that is 10,000 computations of log likelihood. And if you remember, each log likelihood computation involves computation of n PDFs, where my n is 50. My sample size is 50. Okay, so that's why it is taking time. Let us go and read the question during the process while it is running. Okay, so plot the log likelihood with respect to a range of possible values of mu, assuming sigma to be known. Okay, so we are computing the log likelihood. Once it is computed, we will plot it. So for plotting, what we need is persp, then we need mu1, mu2 and z matrix LLMat. Okay, so see here, let us check the dimension of LLMat, 100 cross 100. Maybe we can view. No, view is not going to work. It's too many. Okay, so let me try to show you a few values. Head of LLMat and only 1 to 5 columns, 1 to 6 columns maybe. Okay, so see, for mu1, some value, first value of mu1 and first value of mu2, I am getting this, and so on. Okay, and we want to maximize this likelihood. So we want to see at what point this likelihood gets maximized. So if I draw this perp with tick type equal to detailed, okay, so this is the graph of log likelihood. Can you see now? It's the graph of log likelihood. So somewhere here we have maxima. These are different ranges of mu1. These are mu2. Can you see here? 1, 2, 3, 4. If we rotate, we will see a better version of it. And z-axis, we have log likelihood. So if I take theta equal to say 30 and phi equal to 30, let us see what happens. Okay, so now we have a better version. So I have mu1 in this direction, mu2 in this direction, and the log likelihood graph. Okay, but of course, as I mentioned, locating the actual maxima on a graph is tricky. So we will try to see which entry of log likelihood is maximum. So which dot max LLMat, but I want the row as well as column name, number. So we will do array dot int equal to true. Okay, it doesn't work for which dot max, so I have to write which LLMat equal to maximum of LLMat. Okay, for some reason which dot max doesn't have the facility to directly give array indicator, so I will do which LLMat equal to maximum of LLMat. So the row number 50 and column number 52. Okay, so we want to see the values of mu1 and mu2 at that point. So we will see mu1 at 50 and mu2 at 52. Okay, ideally I should save them somewhere. So what I mean is, suppose I call this as say W, then I want mu1 at W1 and mu2 at W2. Let us confirm that this actually gives me the maxima, and what is the maximum value, that also we will see. So maximum of LL mat is minus 189.3232. So let us try to see if this combination of mu1 mu2 is actually giving me maxima. So if I do by LL at these 2 points, by LL at mu1 W1 and mu2 W2. Oh, sorry, I shouldn't have semicolon, I should have comma. See, 189 minus 189.3232. By the way, this minus sign, some people may be thinking, why am I getting negative sign for the likelihood? It's not likelihood, it's log likelihood. So if likelihood is between 0 1, log likelihood is definitely going to be negative. So don't panic about the negative sign. Okay, now if I want, I can try to compute sample mean and see if my estimate is close. So call means of my data. My data was in YMAT. See, 3.96, 3.95, 1.07. So we are quite close. If we increase the partition size, we will get further closer. Okay. Another way is we have quite a wide range for mu1 and mu2. Now that we know that the values are near 3.96 and 1.09, we can maybe consider a smaller range. Okay, so that can also give me more accurate estimate. So let me try here. Suppose instead of 1 to 7, let me now try, because I know 3.95, so 3.8 to 4.2 and then 1 to 1.1. This is again going to take time. Meanwhile, I hope you are following with these things, you are still with me. As I mentioned earlier, if you are not, now you have the chance. You can pause the video, go back, listen to maybe one statement at a time and try to see if you can follow. Okay, that's actually a benefit of online teaching. You can listen to the teacher as many times as you want, unless of course you get bored in the first time. But if things are not clear, you can always rewind the video. Okay, so this actually finishes our current practical number 7. So we'll just wait for this, and then after seeing this we will sign off. Okay, I know, again I'm mentioning, I know that many of you don't have access to any laptops or computers. Don't worry right now, just try to understand what is being done. Okay, and I'm sending you commands also, so you can have the commands with you. If you get internet connectivity, try to see help of the new commands. For example, try to see help of outer. See couple of examples which are already worked out somewhere. Same story with persp. Try to read all what are the arguments of persp, what they can do and so on. The graph is more or less similar. Okay, see 3.949, so it is almost 3.951 and 1.074, so 1.075. Okay, so it is quite close. Oh yeah, we can also compute log likelihood at that point, actual MLE, and let us see if it is larger. So let me store it in, say, X bar, and we can have by LL at X bar 1 and X bar 2. See, minus 189.3154, this is marginally better than the maxima that we are getting by graph. Okay, so let us stop here.